Yes. So it's my great pleasure to announce a talk by Jorn Wichmann. Jorn is a PhD student at Bielefeld University. He will finish his thesis, to work on his thesis soon. And the good news is that he has already a position at Monash University as a postdoc, so there will be surely more opportunities for interactions in future. The talk is about a very hot topic in stochastic PDEs, in fluid dynamics, and in many other areas about regularization by noise. So please, Jorn, you can start.
Thank you very much. So first of all, before I start, I would like to thank the invitation and so the organizer of the seminar to just be here in Sydney to give this talk. It's a really great honor to meet so many people. Yeah, today I will talk about a pathwise regularization by noise phenomenon, and it's basically on an example of the p-Laplace equation. So in the end, we could basically discuss to what kind of operators we could generalize this phenomenon. And this is joint work with Florian Bechtold, who is a postdoc in the group of Martina Hoffmann-Nova at Bielefeld University. Yeah, and I gratefully acknowledge the funding of the Collaborative Research Center located at Bielefeld University. And the task of the Collaborative Research Center is to study basically uncertainty and find how to handle uncertainty parameters in various models and yeah, questions, basically. Okay, let us dive in. So the p-Laplace equation is a natural equation which arises as soon as we basically minimize this energy. So the energy is nothing but composed out of two ingredients. You have the classical p power of the gradient and something which is of potential type. So it's just a function of the unknown solution u. And usually if we ask, okay, what is the minimum of this j, one could come up with basically schemes to find some minimizer of these equations. And minimizers necessarily need to satisfy the classical Euler-Lagrange equation of this model. And the Euler-Lagrange equation one can compute on the L2 framework is nothing but the classical p-Laplace equation, so the evolutionary p-Laplace equation. So this S is the typical p power, so p minus 1 potential. So if you just take absolute values, this is of kind of power p minus 1. It is a nonlinear quantity, and we just directly see if you put p equal to 2, the left-hand side is nothing but the heat equation. And we need to ask ourselves, okay, what conditions do we need to impose on B, so this big B or the small b, in order to have well-posedness? So in particular, if you just think about the direct method of calculus of variation, if you just want to find the minimum of J, certainly the P growth on the left, which has a positive sign, competes with possible divergence of this big BU towards minus infinity. So in a sense, if you have a finite value here, but in principle could choose B of u to be infinity, then the minimum is basically an infimum, and this guy will not stay bounded. So minimizer will not be reasonable in some sense, at least from the direct method of calculus of variation. And that's why natural questions are, what are sufficient conditions we could impose on the small b, respectively on the big B? So this small and big B are related. This is B prime is nothing but B. To make sense out of this equation. And maybe canonical frameworks are, if the right-hand side does not depend on the solution itself, and more or less elegant condition is to just request that the right-hand side belongs to the dual space of the canonical energy associated to the gradient flow we have here. So if you just test this equation by u itself, you get from the time derivative an L infinity L2 part. From the divergence S part, we get an LP part, or more or less on the gradient level. So if we just take the intersection, the dual space of this guy is kind of this space, or more or less. So we could relax it in some sense, but now we are in a classical framework where we could just cite monotone operator theory and say, okay, if the right-hand side belongs to the dual, we can find a solution which belongs to the classical energy space, which is basically governed by these two guys. And now we could ask ourselves, okay, maybe if f is more regular, for example, really an L2 function, then maybe the left-hand side of the equation itself is already more regular. And this can indeed also be made possible. So if this guy is just f in L2, then we can prove that this guy is an L2 function and this guy is an L2 function. So a priori, if f is in L2, you only know that the object on the left itself is in L2, but not each individual summand. And for this, you really need specific structure on this operator. So it becomes even more difficult if we put here some potential which depends on the solution itself. So now we need to kind of, if we want to apply energy methods, we need to close the energy estimates in order to construct solutions. And if this B just has arbitrary growth, you cannot hope for basically closed energy expressions. As already mentioned, this guy has the natural energy L infinity L2. The second one has the natural energy, which is LP W1P in some sense. So these embed in some space. And if this B of U is not controlled by the embedding space, you are basically out of the game and you put too much energy into the system that is controlled by the left-hand side. And that's why we need to impose usually growth condition on this U. Certainly, we could ask the question, okay, what if we just put a general growth condition on it? Can we still make sense of the equation in some different meaning? And this is the task of today's talk. So actually, if you subtract from U something which is, I call it regularizing paths, but it is more or less really some really irregular function, then you can make sense out of the equation. So then if this B of U is given from this specific structure, so this is the assumption we do at the beginning. If B of U is given by something shifted along this random potential or this regularizing path, then we can make sense of the equation. Okay. But just to explain the differences between basically positive exponents of potentials and negative exponents of potentials, you see that as soon as you have something which is 1 over the solution itself, the state 0 has infinite energy, which basically means as soon as the solution hits 0 at some point, and if we impose 0 degree boundary condition, it is certainly at least hand-wavily explained on the boundary you are close to 0, that it is really hard to make sense of the energy, because then you have B of U on the right-hand side. So how do we do this? This is U, you have L infinity L2 plus some U, which is LP W1 P0, kind of. And this is like B of U times U. And if this guy is basically infinity because U is at some point 0, then the left-hand side will be more or less infinity. And that's why you cannot use energy methods. While on the right-hand side, usually the state 0 is nice, because there you just pump nothing in the system. So you basically have control that if this guy is bounded, then the left-hand side will be bounded, and then you can basically come up with closing estimates. And just to give you some history on the development of classical monotone operator theory, yeah, it basically traces back to the early works of Minty and Broder and Larry Livon, which treat it the elliptic case. So just put some elliptic operator and you ask yourself, when is this equation invertible? So basically you need to characterize the equation AU equal F, and you ask yourself, okay, when is this operator A surjective on some function space? And as soon as it's surjective, then you can invert it just by taking something from the pre-image. The parabolic case was then basically studied by Kato, Bresi, Babu, Otani, but also recent works of Hauer, where they studied different basically perturbations of general monotone operator in the parabolic sense and try to make sense out of if you perturb your equation and you want to still find solutions. And the stochastic case is very popular, and it traces back to the results of Pardo or Krylov and Gosowski. And I can firmly recommend that the book of Pivot or Göckner, or the more recent book of Liu and Göckner, where they basically give a variational framework to solve stochastic PDE, monotone PDEs. And just to make clear, these papers usually consider weak solution. That is, they work on the triple and the Gelfand triple V prime, not on the intermediate scale H one has here. But the recent paper, or more or less recent paper of Benjamin Guess, he did the construction of monotone equations in the strong framework. So he did gradient flow equations and derived really strong solutions. So solutions you could express pointwise almost everywhere. And exactly this pointwise almost everywhere usually is something more which one can use to then later do numerics or. So the general spirit I want to convince you is, well, posters per se is a nice theoretical result, but in the end, if you want to see solutions, you need usually something more. And this is captured by strong solutions. Okay. So now regularization by noise is such a big topic. And I try to capture at least some branches of this fancy word regularization by noise. So the first result I want to mention is regularization by transport. And this has become very popular in the study of fluid equations. So first of all, one should have in mind, when studying fluid equations, the famous name Navier-Stokes equations usually pop up, and people try to answer, are these equations well posed in 3 dimensions? And so far, no one has really come up with a satisfactory solution. But people try to understand how is the influence of random perturbations of these models, and maybe it is exactly the randomness that is the missing ingredient to come up with either well-posedness or ill-posedness. And maybe surprisingly, if you put right structures on the right-hand side, so if you have some equation du minus, I don't know, au dt, and you put really some gradient, some transport noise, which is like a sigma dot gradient u circ dw. So you interpret this in a Statonovich sense. If you put the right sigma and the right dw, you can enhance the regularization properties of the solution, because one can compute that one has an additional dissipation which acts on the scale of the Laplacian. And this has been exploited by several authors just to make well-posedness more feasible, because exactly the additional dissipation leads to usually stronger well-posedness results. And just to mention a few, for example, in the paper of Benjamin Guess, Teresa Lange or Antonia Agresti, these are all more or less recent works, and there's many, many more. So it's very, a nice topic to have a look at. The second part I called regularization by blurring. So if you basically have a PDE or an S or an ODE and try to make really sense out of singular perturbations. So if you have just merely L2 integrable right-hand sides or even worse, usually point evaluations do not really make sense. And then the question is, how do you come up with an effective construction of the algorithm? So maybe classical Picard iteration do not converge a priori. So you need to come up with possible substitutions to make the things work. And this is exactly what we also will do. And I called it just regularization by blurring, which means that if you shift your solution by a random path, it no longer sees point values, but more or less looks also in neighborhoods, which basically says that the point singularity will not be evaluated at the singular point, but in some sense, it will be stabilized by the neighborhood around it. And this has been used by different authors. Just to mention a few, the works of Rubinelli and Gagliardi and Liu and Shen and Florian and Martina Orfanova. And yeah, you should check these out. They are really nice papers. And going back to strong solutions are basically needed in order to do numerics. Also, numerically, it can be helpful to introduce noise. And this has been done, for example, by Kruse and Wu or by the Reitios and Gerencesa, which, so they come up with random algorithms that are more stable for irregular approximations. So as soon as the general rule of thumb is, if you have something smooth you want to approximate, stick to the old algorithms. But as soon as you leave the smoothness regime, you should modify your algorithms and choose robust ones. And robust ones are either, for example, by randomization or by different averaging techniques, for example. And now I try to explain to you why freezing usually increases the regularity of what we want to construct. So if you just remember the equation, on the right-hand side, this guy appears. And if you want to understand how the right-hand side might look like, we just naively say, okay, what about, we don't integrate about this shifted path, so both functions depend on time. What happens if we just freeze one of the parameters? And naively speaking, if this guy on the which we put inside this integral is just continuous, in the limit, this guy will just coincide. So if s is small to t, then in some sense it's okay to freeze because they are anyhow close. So, but actually what happens if you freeze? Suddenly you can exploit nice properties of W, because W itself, if you just rewrite this integral as the push forward, so basically we just do not integrate about the function values of W, but about the interval time W spends in a certain time spent in a certain set, we can rewrite it as this integral equation. And as soon as this measure has a density with respect to the Lebesgue measure, we can basically rewrite this as nothing but B frozen minus what we have here times the so-called local time. So this measure is called occupation measure, and this guy is the corresponding local time. And just a brief observation is that effectively, if we freeze this guy, it looks like a convolution with the local time. And just to get a feeling how one can think about the local time. So you just freeze time parameters, let's say S here, T here, and then you could either integrate about over this line and just evaluate the function values we have here, or we integrate over this line, which is now the real line, and we ask ourselves how much time does the process, this red line, stays inside the region, which is, for example, this blue one. So we need effectively like here something, maybe here. So it's just computing the time we spend in it. And the gray dots, so the gray underlined here, these are just 100 different realization of, I think I plotted here the Brownian motion. So 100 different realization could in principle look kind of different. But if we just look at the distribution of how much time those guys spend in certain areas, this looks more or less like a nice function. So if you now take more and more, this will probably smooth out and give you some nice function here. And this is a function which depends obviously on the position of x, but also on the time horizon you look here. So this guy is basically L T of S, or maybe we need to divide this by so maybe it is this. I don't know, but one or the other. Yeah, and usually, if we have a convolution, convolutions upgrade regularity in a sense. If B is irregular, we can cope with irregular B just by imposing conditions on L. Because convolutions says that basically the function that comes out here is the sum of the regularities of what comes in, and not only the minimum or something. Now the question is, okay, what does it help to freeze and then to basically rewrite this guy? Therefore, we need to reconstruct what we want. So the right-hand side is nothing but this guy. But certainly, because the integral is additive, so we can just rewrite this as an arbitrary partition per se. So we just take some partition. It is valid for any. And if we just say, okay, this guy is the blue guy, then we would be, okay, this is just a different way to rewrite the integral. But if we now assume that effectively each of these guys can be frozen, then we just define this guy to be a of tk minus 1 tk, which says, okay, our original integral is like the sum of the individually frozen guys. And the question is, when is this the canonical definition? And for this, we need the Sewing lemma. The Sewing lemma tells us as soon as it is okay, so maybe I draw an image. So we have here time s, we have here time t, and here's some point r. For classical integrals, it is we can split it up into arbitrary points. That means that it doesn't matter whether we go from point s to t directly or whether we go from point s to r and then from r to t. Which tells us the delta operator, which is nothing checking but this condition, how costly is it to jump directly from s to t, or we just do the in-between step. If this function is just sufficiently regular, that means that it decays with a rate of 1 plus something, then it is okay for the Sewing approximation, and this guy will then converge to something which basically recovers the integral. Because what should the limit of these guys be? This is a linear operator acting on these guys, which will give you a one-parameter family, which is in fact kind of an integral. It is a linear operator acting on what you put inside. It is additive, and it fulfills basically the definition of an integral. But it is constructed in a different manner. And exactly this is, so if you compute the delta operator for the B, you see that the delta operator is just 0, so it trivially satisfies this condition, and effectively you get that. So you get that the 2-parameter family constructs a 1-parameter family, which one can think of as the integral, and you can evaluate this locally. So this is kind of a Taylor expansion. So if you subtract 2 points of this reconstruction, so of the Sewing, you get basically a s of t, and you have an error term of size 1 plus alpha. And just if you see this is valid for all arbitrary t and s, if you just sum up both sides, you see that this guy in a sum will converge to this guy, respectively this guy, and this guy will just go to 0. So it is really just some local description of what you want to have, and you allow for some error term. Yes.
So alpha has to be strictly greater than 0 then, right?
Yes, alpha needs to be positive. So actually, you could put here some O of t minus s, but it's just convenience to give a positive alpha. Yes, and why does this help? So let us first, we try to use energy methods to construct solutions. And we start from the strong energy estimate. That means that for simplicity, assume we have a strong solution which fulfills this equation. Then natural energy estimates by just squaring both sides and computing that the left-hand side is nothing but a nice bound. So in some sense, you could compute if this guy acts onto this guy, you do one integration by parts. So we have 0 boundary conditions. This is an assumption, of course. Then we see that we have a nice control on the time derivative of the function, on the gradient of the p's power of the gradient in L infinity. And we had to have additional information on the divergence. What do we need to pay? We need to request finite energy of u naught. And somehow we have still on the right-hand side something which depends on the solution. So this is not a closed energy estimate. We need to somehow find a way how to estimate this guy, which is maybe controlled by the left-hand side. And then we are good to go and say we can now do a stable approximation. And just as a brief observation, the time derivative automatically gives us Hölder regularity of the solution. At least the semi-module, so the semi-norm is controlled with a constant 1. But we will see that these Hölder regularity is useful when we want to basically estimate the swing we have done before. So, and how do we find out that what we want to have can be sewed together? So we want to reconstruct this guy. So we just freeze this guy, what we put inside by, so this is the integral from 0 to t. We just expand this along some arbitrary partition and just freeze the guy what we put inside here. And we just call these guys AST. So if these are, yeah, exactly. These ARTs are nothing but these guy what we put inside, but we have already seen that if this guy is frozen, we can express this as a convolution. So we have b squared convolved with L at ST evaluated at U of S. And now we need to think about, okay, this A of t and ST can be sewed together, provided the delta operator is sufficiently regular. So what do we compute? We just compute the delta operator. And we see that the delta operator is the same function here, acting on different values. So first on U of S and U of R. And this can just be naively estimated if we just take the Lipschitz norm of the function. We just call this guy f, and you put here the Lipschitz norm of f. And what remains is U of S minus U of R measured in L1. So regularity in L1 gives you now here at least some regularity in time. So we just take this to the power 1/2, S minus R to the power 1/2. So we see we have already 1/1/2, but we need 1 plus alpha in order to sue. But now we use that this blue guy also has regularity in time. So effectively, we divide this guy by S minus T to the power 1 alpha plus alpha. So we get here 1 plus alpha, which now says that, okay, these A's can be sewed together and give you something which is an integral. And here it is crucial. So usually this guy cannot be C1 plus alpha. So it is really important that we get at least a tiny bit of regularity from the solution itself on the right-hand side. So we really need here some C alpha. Usually this alpha needs to be positive, but continuity is not enough. Yeah. And now, how does this help? So actually, we just estimate this guy by what we just computed. So basically, we put some B, some L, and now instead of the Hölder norm, because the Hölder norm is dominated by the norm on the time derivative, now we see that the red guy is on the left and the red guy is on the right. So basically, we just cancel one power, roughly speaking. And now we see that the right-hand side does not depend on the solution anymore, which means that we can now obtain a stable approximation in the energy norm here, which is now our ansatz space. So this is just X. Now we basically find the construction because usually we need to identify. So yeah, that's
one problem. When you divide, you have the gradient U not in front of you. You cannot divide so easily. You must probably apply Young's inequality with a half, and then you.
So actually, what you can do is you just forget about these. These are positive.
Yeah, but you have on the right-hand side still the gradient U not, and when you divide, then you will have.
Yes, you don't divide, but you use something like A squared less B plus CA. This already implies some inequality.
Yeah, but when you apply on CQ in a smart way, Young, so for instance, instead of A times B, you make an epsilon, square root epsilon of A times B divided by square root epsilon. Then you can choose epsilon nicely.
Yeah, okay, yeah.
And then you can cancel this. So you will keep, nevertheless, that there is written dt U squared. You will keep it, but you can cancel it with the other time.
Yeah, exactly. That's actually what comes out in the end. I mean, you could do Young, you could, here are many ways to do this. But that also explains why in the end you obtain your square.
Exactly.
Yeah, that's true. And so a natural candidate to look for solutions is the natural space here. So we request a function is now called robustified solutions. If we have the natural regularity, which means we have control on the time derivative, we have control on the L infinity W1 P norm, and we have control on the divergence of S. And we want that the integrated equation is valid. So ut minus u naught, then the p-Laplace is equal to the suing of u itself. And the suing is nothing but the limit of these germs. And the right-hand side is, so in some sense, we can make sense of singular equations if we interpret the right-hand side in the right way. This is the statement in the end. Yeah. And this is exactly what we have. So basically, if we now want to make well-posted theory, we can do it for this kind of equation. So we have zero boundary conditions. We start with some initial function, and now we can make sense out of exactly this equation. And we need as an ingredient sufficiently high initial regularity, which means that u naught should belong to the energy space. So I should probably put here a 0. W needs to be adjusted to the parameter of B. So basically freezing the parameter B with a suitable integrability condition. Then we need to find a W which matches the condition. So exactly if B is L2R, we need that L belongs to W1R prime with some time regularity. And one can check that, for example, for fractional Brownian motions, such a regularity statement is possible. So one has not a non-trivial statement or a statement about a null set, but there exist examples for W's that satisfy this. And the statement then is, yes, you find a solution, and this solution has a quantified a priori bound in terms of the parameters you put inside. And this then looks like this is nothing but the norms on the space. So this is the canonical energy of where you seek for strong solutions. And you expect that all the ingredients you have assumed appear on the right-hand side, because otherwise you wouldn't probably assume them. And just as a nice side observation, if this B a priori is regular, so we just assume B is nice, then you can just check that the classical suing, so that first of all, the time derivative exists just by the equation. So these guys, two guys are differentiable. That's why the suing itself is differentiable in time with values in L2. And if this B is regular, then you can check that the derivative evaluated at the time is nothing but B shifted along these paths. So for smooth B, we can identify, but for non-smooth B, it is not clear how this guy then looks like. But anyhow, it fits to the theory for smooth B. Okay, and just to shortly comment on how to basically perform the proof, I've showed already to you how the freezing gives you basically regularity via convolution, how the suing then basically makes from local approximations goes to global approximation. And now we just need to say, okay, why was it okay to do all this? And this is basically, we just approximate our equation by a smooth system. So we just mollify, for example, B by some B epsilon. So it's nothing now a smooth potential, which is bounded. And we only require that B epsilon converges to B in L2R. Because L2R appears on the energy bound, that's why we need only that this norm is bounded, nothing more. And then we need to basically say, okay, for each B epsilon, we can now find a unique U epsilon. This is classical theory. As soon as the right-hand side is Lipschitz and of linear growth, you just get, so linear growth gives you existence of strong solutions. Lipschitz gives you uniqueness of strong solutions. So U epsilon exists. So now you have basically an approximation sequence of what you have, and now you just need to find some limiting object. And this can be done by exactly the new a priori bounds. These are stable in epsilon because you assume that B epsilon converges to B. So this guy is bounded by B. And now the right-hand side does not depend on the approximation anymore, which says, okay, now we can subtract subsequences, and all these guys will at least formally converge weakly or weakly star. But luckily, we can also identify the suing. If we know that B epsilon converges to B in L2R, and U epsilon converges to U strongly in this space, then you can check that also the modified suing evaluated at the U epsilon converges to the suing of U itself, so on the non-modified B. And as soon as you can identify the right-hand sides, you can use the Vinci trick to identify the monotone operators. So because you also need to identify whether S of gradient U epsilon really converges to S of gradient of U. But this can then be done by standard theory. Yes, and just as already said, there exist really W's that satisfy the conditions we have in the theorem. And for example, in theorem 3.1 in the paper of Hauer and Perkowski, they give precise conditions on the parameters. So if you have a fraction Brownian motion with Hurst index h, you require it to be less than 1 over the dimension. Then exactly the local time L exists, and you can get a bound on the regularity. And effectively, you can treat how much regularity you want to measure on the time parameter or how much you want to measure on the space parameter. And basically, you can choose alpha big enough and beta big enough until you reach basically C0 1/2 plus delta and W1 R prime. So you just need to choose that H beta should embed into W1 R prime. And alpha needs to be bigger than 1 over delta. This is a condition on H. And just to give you an example, for example, we can treat potentials like 1 over alpha. But unfortunately, because in the end, B is estimated on the full space, we also need some decay property at infinity. So either you truncate this guy or whatever. But usually the the key point of singular perturbations is really that you have singularities sitting in compact sets. So it's not about behavior at infinity, but about behavior in zero, in a sense. And this is more or less, I would say, a necessary condition, but it is really due that we see an unbounded domain where we look at in the end. Just to give a different motivation for the equation, the same model also appears just as a transformation of a classical stochastic PDE. So if you just look at this PDE, where the p-Laplace equation evaluated at this potential, possibly very, very bad, you shift it along this path of W. And since now we can construct U, we also can construct V by just adding this W. W is given to us. So we can make sense out of this equation. Yeah. And I need to admit, originally we started studying this equation. And after this transformation, we end up by our condition. But effectively, you can study. It's really an effect that you just see on the right-hand side. It doesn't really matter on what you put here on the left-hand side. Because at no point we have used that we have really a p-Laplace operator sitting here, but more or less we needed that the time derivative of u is controlled, that you can identify the solution. And yeah, I think that's it, basically. Okay. Just to summarize what we have done. So basically, we have seen that locally construction, so yeah, the suing justifies the freezing. So suing says that you can reconstruct local constructions to global objects. And freezing then says, okay, locally, you have some regularization just by exploiting the local times of what you subtract. Overall, this leads to stable energy bounds, which have not been there before. So we have some new energy estimates, which are really stable in the approximation. And as already said, the specific structure of the p-Laplace operator doesn't really play a role. So we need that kind of, we have nice spaces appearing. So we have certainly used that the time derivative of u times the p-Laplace, where at u, whoops, sorry, that this guy is nothing, so integrated somehow the time derivative of a norm, so that we still have some sign conditions in a sense. So, but you could also put here different operators, which have probably then different sign conditions. But yeah, this is maybe for future research. And the statement then is basically, okay, if we have a singular potential, but it is shifted along something which might be very random, one can construct so-called robustified solutions, or we called it at least so, that the equation can make sense out of pointwise. So this equation can be interpreted pointwise in time and space, not only tested, but we do not know whether this guy up is basically justified. For smooth potentials, you can identify, but if B is non-smooth, you cannot see what this guy is. Yeah, and if you want to read more about this, yeah, you can check out the preprint. And basically, that's all what I want to tell you. And I'm waiting for questions.
So let us thank the speaker first for a fascinating talk. And are there any questions?
I have a question. So in this way, you construct the solution, the existence. Do you have any like a uniqueness result for this set of solutions?
We tried to prove uniqueness, but we haven't come up with an answer yet. So it could be that they are unique. It couldn't be. Could also be the other way around. I don't know. Yeah. Short answer: no.
Yeah. Another question. So here, I suppose the spatial domain is bounded. Right?
Yes.
Do you have any idea how to do for the unbounded region? say the whole R.
One needs to trace whether the estimates. So assume one use embedding estimates, one can, in the unbounded case, can only use the critical exponent, right? So that you have like W1P embeds into P star and not below it. And I think usually we just didn't carefully do this. For example, this L1, L2 estimate is only true on bounded domains. As to short answer, I don't know. So I think something is possible, but one needs to check carefully how the constants look.
Very good, thank you.
Thank you very much.
So then can I ask a question? Do you hear this? Yeah. So I mean, so with you freezing, you start with the lower end, is it right? So you freeze basically US. So when the integral goes from S to T, then you always, in order to regularize at the end with local time, the B of U minus omega, you choose then B of US, the lower end. What happens if you choose the middle?
So actually you can basically put arbitrary things there. So it's just convenience to choose, for example, the lower point. Yeah, exactly. So I also think that you can just put some abstract function value, and in the end you compute what, for example, the minimizer of these guys should be. So for example, if you approximate a classical integral, you should, for example, want to choose the midpoint because it is usually more accurate in terms of quadrature rules. So if you just approximate some integral, just allowed to take one function value, you should probably take the midpoint because it is higher order in a quadrature from quadrature point of view.
Yeah, I still have another question. Okay, so in your estimates, the coercivity of the p-Laplace operator is only needed for your compactness result, is it right? Otherwise, what you need is the estimates, the Hölder continuity estimates with the time derivative. And because you are having an interplay with B of U minus omega, you know, and with the time derivative. So the coercivity is important for you, basically, of the operator.
Yes, so basically we need strong convergence in the end in this CL1 sense. So where was it? It is exactly in the identification of the nonlinearity. Where did I put this? This is in the proof, I think, here. So we really need this strong convergence. And if you want the convergence C and L2, we also need the strong convergence C and L2. And yeah. So basically for this, we need kind of that W1P compactly embeds into L2. But if you want to do this on lower sense, we could ask here for convergence in L1, then only the integrals converge in L1, which is fine. And then this is always the case on bounded domains, of course. And then you can do it. It's just the question how you want to interpret the equation in the end. If you just care about pointwise interpretation, you don't need whether L1 or L2, it doesn't matter. But of course, if you want to take norms, then it does matter.
Thank you, Ben. Thanks.
Any other questions? Who wants to comment or ask questions? There can be many questions. Perhaps I would like to start from a comment when you showed literature about blurring by noise at the beginning. Then perhaps one should mention the paper that started this idea, and it is a very old paper by Veretennikov. I don't remember exactly the time, but it was in 70s probably, or 80s at latest. And he showed that stochastic differential equations can have blow up, say, suppressed by noise. Yes. So this is a much older paper than you show here. And also a question, so the whole theory is of course purely scalar, yes, am I right?
Yes, yes.
Yeah, you cannot do it for a system because there is a then question, what is the local time, yes?
Exactly.
Yeah. And maybe one last, in your last example, where you showed this with linearly entering noise.
Okay.
Yes, so here, even if W is a Brownian motion, then solution is never Markovian. In order to have, say, Markovian solution, you would need to have dW on the boundary as well, yes? And then is it possible to do anything in this case, in such a case?
So I didn't quite get the question. So here we need to have also W on the boundary.
Can you have white noise on the boundary?
Short answer, I don't know. I mean, this dW kind of needs to be interpreted that you integrate the equation in the end. So you have W really. So it's not like you have V is Brownian motion, so it's some dW.
Yeah, I understand. That would be somewhat different equation. Yes?
Yeah, exactly.
Yeah. Okay. Are there any other questions?
Maybe one comment, as you did
Yeah. Okay.
in the literature, in the deterministic theory, you should mention also Lyon's in the parabolic case, because Jacques Lyon's, he did not only the elliptic theory, also the parabolic one, quite forward.
Yeah.
There's a very famous book from '69, I think. And there he did also the parabolic case.
Yeah, I think this whole list can be extended to I think 5 slides.
Quite a lot of
contributions.
So the list is not complete.
Yeah. Makes sense. Let's say I just selected a few and that's it. But thank you for pointing it out.
Are there more comments, questions? If not, then we can close this meeting, but everyone is invited to coffee break online, and the link to the coffee break is provided in the reminder email. So see you all there in, say, a few minutes. Okay, and now I will close the meeting. Bye.
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 Thank you, Ben.
Thanks. Bye.